Okay, thank you very much for having me here. So I'm going to talk about how to determine the roof age with deep learning and why that's important for solar and therefore for climate change. So I'm going to spend most of this time trying to convince you that that's a problem worth looking at, and then tell you a little bit about how we solved it and what we might want to do next. So first of all, I probably don't need to convince anybody in this room, but why is rooftop solar important? A few numbers. It's estimated that in the next 30 years, it could displace about 25 gigatons of CO2. It's a top 3 source of renewable energy, and it's one of the top 10 interventions for climate change. So we'd obviously like more of it. And how do you get more of it? You do that by making it cheaper. So here's a plot showing on the yellow curve is sort of the price per watt for installed solar, and then the blue bars are the amount of solar you installed every year in the U.S. And there's sort of a very clear trend, economic trend, that as solar gets cheaper, you get more and more solar installed. But now we're at a point where sort of the material costs, like manufacturing, have gone down so much that the soft costs now account for about 60% of the cost of installing solar. So that includes labor, permitting, customer acquisition costs. In fact, your customer acquisition costs in the U.S. account for about 20% of the total cost of installing solar, which is really high. So it's a prime sort of target for further reduction in costs, is to try to reduce customer acquisition costs. And the roof age, and of course, there's lots of important criteria for determining what's a good building for solar. But I'm going to convince you that actually the roof age is another one that's important, and it hasn't been studied so far as I can tell. And that's because PV systems last about 25 years, and roofs, particularly for like commercial and industrial buildings, maybe not for like very good Swiss roof, but for most roofs here, they last for maybe 30, 40 years. And so the best roofs are about either new roofs, which will last for the lifetime of the array, or roofs that are quite old, in which a solar developer can sort of replace the roof and install solar in one shot. And that's actually their favorite. But we estimate that about 20% of CAC is wasted on buildings that have the wrong roof type, because a solar developer is going to spend a lot of sales and marketing money to basically get to sit down with the building owner, and then later find out that the roof has sort of the wrong age. And basically, because labor is so expensive, that if you want to, halfway through the lifespan of the array, take off the solar panels, replace the roof, and put the solar panels back on, you've kind of killed the economics of the solar project. And there's much less of a financial incentive for them to install solar. So it's a really important criteria that solar developers care about, in addition to other things like size of the roof and solar potential and other factors, electricity consumption. And so we kind of did a back of the envelope calculation to estimate that if this problem was totally solved and all solar developers knew the age of the roof before they were trying to sell solar, they would the amount of money that they saved would correspond into an increased deployment of solar that should displace about 760 megatons of CO2, which, to put in context, is equal to about the total emissions of Switzerland for the past 20 years. So it's not a gargantuan number, but it's also not a small number either. And if we had 100 such interventions, then we'd sort of be talking about pretty large numbers in terms of CO2 displaced. So I have a sort of computer vision background, so I'm thinking, okay, how can we determine roof age from satellite image? But if you look at a single satellite image, it's really hard to tell. Is that roof 2 years old or 10 years old? Can't really tell. And if you look at another satellite image, it's still fairly unclear. But if you keep going back in time, then you notice, and sort of an interesting fact, which is that you go back far enough, the roof was likely replaced at some point in time. In this case, it was replaced between years 2015 and 2016, which tells you that roof is about 4 years old. So this is sort of the main insight that we use to try to solve this problem. I mean, obviously you can see it with the human eye looking at Google Earth, but we want to train a machine learning algorithm to do that. So we need to collect a large data set of sort of roofs that have been replaced and roofs that hadn't. So we use public building permit data to identify a lot of buildings for which the roof had been replaced, as well as buildings, sort of the null case where they hadn't been replaced. And we combine that with historical satellite imagery to build up a data set that contains about 1,600 images. There's an image of a given building every year from 2012 to 2018. So about 230 buildings. The building permit data is pretty noisy, which is why you can't really use that it's noisy and incomplete, which is why it doesn't really solve the problem, but it was enough to kind of bootstrap the data set. So We also hand cleaned it, and it contains buildings with roofs, re-roofs and no re-roofs, and I have information for sort of getting that data later, which we make available for future research. So the training, we originally wanted to solve this in an unsupervised way. So we have it sort of unsupervised VAE that embeds images into latent vectors and then decodes them. We found it was also important to add a sort of supervised component to that. So this cartoon is, each of these is sort of representing neural networks. But the supervised one, it takes in sort of two latent vectors corresponding to the same roof from 2 different years, and it predicts the probability that the roof had been replaced between those 2 years. And so at inference time, we take two consecutive images, we encode both of them into latent vectors, and then we classify whether or not we thought the roof had been replaced from image 1 to image 2. We do this for all the years in our sequence, and if the probability is less than 0.5, we say, okay, the roof wasn't replaced, so it's probably older than the oldest image in our data set. Otherwise, we take the pair that maximizes that probability. So our sort of state-of-the-art results, which is sort of a joke because it's the only art, is first I'll show kind of a couple examples where we predicted the year correctly. Here is sort of a failure case, which you can see the image where the roof was replaced. It's foggy or blurry or something, and that's sort of one of the challenges of this problem, is that every year that the image is taken, usually it's under different lighting conditions, different weather conditions. There's always various stuff happening on the roof besides the roof being replaced. But I think with more data, this was a relatively small data set, we can sort of learn the space of variance that we care about. And so overall, we got on our test data set got to an average error of about 0.68 years, so we were able to predict the roof age fairly accurately. So the next steps, the most straightforward way to kind of improve this approach is just to expand our data set, which was kind of the most laborious part of this task, but it's the most straightforward way to improve it. We could additionally do additional pre-processing, like segment out the building footprint to remove the various junk around the building. Most of the time we sort of zoomed in enough that wasn't an issue, but for smaller buildings, residential ones, it would be important. We could try to tackle estimating the roof age from a single image, which would be hard, but maybe possible. And most importantly, sort of bring the solution to market. Like echoing Lynn's comments from yesterday, you really have to get these things deployed to make an impact. So the kind of high-level takeaways is that, one, machine learning was critical. We tried feature engineering approaches and various other approaches, and the learning was really important because of all the variance, lighting and weather variance that takes place in this problem. I think it constitutes a fairly high impact, per dollar, in the sense that, actually ramping this up so that it works kind of on a global scale and getting it deployed is not actually that hard, as we've seen with projects like, Project Sunroof or whatever have attempted things like this. And that the impact is sort of greatest if we work closely with industry. I never would have learned about this sort of obscure problem that solar developers have had I not been sort of working with solar developers in the first place. And so, I acknowledge my collaborators. One of them was going to give a talk today, but that got canceled, so you can ignore that. And our solar collaborators who we worked with, who brought this problem to our attention. And of course, I'd like to thank the conference and track organizers, Lynn and Nicola, for putting this nice track together. So thank you. That's my email, and that's a link to the archive paper, which includes a link to the data set if you're interested. If you're interested in learning more or collaborating on anything, happy to just reach out, happy to talk more. Thank you.